les damos la más cordial bienvenida a esta conferencia organizada por el TEC-NM CENIDE y el IEEE Capítulo de Comunicaciones, sección Modelos. Realmente es un honor para mí presentar al doctor Carlos Cordeiro, quien es conferencista distinguido del Instituto de Ingenieros Eléctricos y Electrónicos, IEEE, y quien nos va a compartir una charla muy interesante. Pero antes le doy la bienvenida al maestro de Ciencias Jesús Vázquez, quien es vicepresidente del Capítulo de Comunicaciones, sección Modelos del IEEE, y quien nos va a dar un mensaje sobre el IEEE y los beneficios. ¿Okay? Buenas tardes, maestro. Bienvenido.
Hola. Hola, hola. Muchas gracias por su asistencia. Voy a permitir, antes de pasar a la ponencia magistral, explicarles qué es y qué hacemos en el IEEE. Esta plática que nos hicieron favor de recibir aquí en CENIDE ha sido posible gracias a la contribución de IEEE y el programa de conferencistas distinguidos. Esta plática la he titulado el IEEE y sus sociedades técnicas, conectando pasiones y profesiones y oportunidades para universitarios. Para los que no lo sepan, seguramente ustedes que son estudiantes de posgrado, IEEE son las siglas del Institute of Electric and Electronic Engineers, la sociedad de ingenieros más grande del mundo. Inició en el año de 1963 en Estados Unidos y ha ido creciendo orgánicamente hasta ya tener alcance mundial. Prácticamente todos los países que tienen que ver con tecnología o con su desarrollo o su uso tienen algunas secciones o capítulos IEEE. Actualmente conecta a más de 400,000 miembros a nivel mundial. Y probablemente ustedes que ya están en posgrado saben que IEEE es líder en la publicación de estándares en las distintas especialidades y en conferencias y publicaciones de tipo técnico. Para que se den una idea, estas son las sociedades técnicas que tiene actualmente IEEE. Ya no nada más es enfocada a eléctrica y electrónica, sino que hay sociedades en una diversidad de especialidades, desde comunicaciones, ingeniería médica, biología, aplicaciones industriales, robótica, automatización de procesos industriales. Las que están subrayadas en amarillo son las sociedades técnicas que tienen presencia actualmente aquí en el estado de Morelos. Al ser miembro IEEE, ustedes pueden pertenecer a los capítulos técnicos que están formados localmente y no solamente tener acceso a los beneficios de las publicaciones, cursos de especialización, certificaciones, sino formar parte de las actividades técnicas que se organizan localmente. Actividades como la ponencia que vamos a presentar el día de hoy a continuación con el ponente que nos visita de Intel Estados Unidos. Al ser miembros IEEE, pueden tener acceso a estos beneficios, como son acceso a las revistas de alto nivel, como son el IEEE Spectrum, que es de divulgación, y las revistas o publicaciones periódicas que tiene la sociedad técnica de la cual ustedes se decidan afiliar. Adicionalmente, cada sociedad tiene cursos en línea, tanto en línea como presenciales, tiene conferencias periódicas, y algunas sociedades tienen herramientas y bases de datos técnicas a disposición de sus miembros. Y a mí personalmente lo que más beneficio le veo a ser parte de la comunidad IEEE es tener acceso a los programas de desarrollo continuo, a tener oportunidades de networking con personas y expertos a nivel mundial y oportunidades de voluntariado y de liderazgo. Sobre todo, actualmente IEEE está promoviendo mucho el acercamiento con los estudiantes, que son el futuro de la tecnología, y continuamente hay convocatorias para concursos, para asistir a congresos, hay hackatones, muchas actividades que son de interés para ustedes. Y yo el mensaje que les quiero transmitir es que muchas veces pensamos que lo que hacemos en México no es suficientemente bueno. Quítense esa idea de la cabeza. Ya hemos tenido casos de éxito aquí en Morelos que realmente tenemos la capacidad de estar en eventos y a nivel mundial. Entonces, una de las principales ventajas que yo he visto para los estudiantes es formar parte de los capítulos técnicos y acceder a todas esas oportunidades que hay. Por lo tanto, los invito a que se afilien, sean miembros de IEEE. Actualmente IEEE está celebrando la Semana de la Educación, un evento que se hace anualmente, y gracias a esto tenemos descuentos para membresía IEEE. La membresía es anual y actualmente para las universidades que son de aquí de Morelos, tiene un 75% de descuento en la membresía IEEE, y yo que soy presidente del capítulo Comunicaciones, traemos para todos los estudiantes membresía gratis con los códigos que tienen aquí en pantalla. Si quieren mayor información, yo voy a estar disponible después de la ponencia por si quieren acercarse a platicar. Muchas gracias y cedo la palabra a Yasmín, que nos va a presentar la semblanza del ponente que nos acompaña.
Atrás. Muchas gracias, maestro, por su mensaje. Ojalá.
Muchas gracias por el mensaje. Esperemos que muchos estudiantes se animen y se afilien al IEEE. Bueno, pues ahora sí llegó el momento de presentar al doctor Cordeiro. El doctor Carlos. El doctor Carlos Cordeiro es miembro del Intel Corporation, en donde se desempeña como director de tecnología inalámbrica. El doctor Cordeiro lidera el equipo global de estándares y ecosistema de conectividad inalámbrica y es responsable de definir la estrategia tecnológica de próxima generación, la participación en el ecosistema y la planificación regulatoria. Ha desempeñado un papel fundamental en el desarrollo, la estandarización y la producción de varias generaciones de Wi-Fi y Bluetooth, habiendo desarrollado innovaciones tecnológicas importantes presentes en miles de millones de dispositivos inalámbricos. Es miembro IEEE y preside la Junta Directiva de Wi-Fi Alliance, la organización que define el Wi-Fi. Debido a sus contribuciones a las comunicaciones inalámbricas, ha recibido diversos premios, entre ellos el prestigioso premio CTO del año de la Wireless Broadband Alliance en 2022, el medallón de estándares IEEE en 2017, el premio Intel al inventor del año en 2016, el premio al ingeniero destacado del IEEE en 2011 y el premio al nuevo rostro de la ingeniería del IEEE en 2007. Es coautor de 2 libros de texto sobre tecnologías inalámbricas, publicados en 2006 y 2011. Ha publicado más de 130 artículos solo en el área de las tecnologías inalámbricas y posee más de 450 patentes. Es editor en jefe de la revista IEEE Communication Standards Magazine y se ha desempeñado como editor de varias revistas, incluidas IEEE Transaction on Mobile Computing, IEEE Journal on Selected Areas in Communication, IEEE Transaction on Wireless Communication, IEEE Wireless Communication Letters y la revista ACM Mobile Computing and Communication Review. El doctor nos dictará la conferencia Future Wi-Fi, Deterministic, Smart and Secure. Good afternoon, Dr. Cordeiro. Welcome to Mexico.
Thank you. Thank you for the kind introduction, and thank you for the warm welcome to Mexico. I appreciate it. It's always great to be here. So I'm going to be, my Spanish is not good at all, so I'm going to be speaking in English if that's okay. So today, as the title suggests, I'm going to be talking to you a little bit about the future of Wi-Fi. In my presentation, I just have one slide, which is the next slide, where I'm going to be talking about the present, but everything else is going to be about the future. Just to set the context, I hope everybody can see the slides. Just to set the context for where Wi-Fi has evolved. So Wi-Fi is about roughly 25 years old. There have been several generations to Wi-Fi. The latest generation was launched December of last year. That was Wi-Fi 7. So that's the one that you see at the rightmost. I'm going to walk through the other ones, but just so you know where we are today. We are in Wi-Fi 7. That's the latest generation, launched December of last year. If you walk backwards, and what you see is we've had several generations, and I'm showing from Wi-Fi 4. Why? Because Wi-Fi 4 is the technology that is mostly, a lot of devices that you buy today, if you think about IP cameras or thermostats or Alexas, some of you use Alexas, many of those devices, they're going to be using either Wi-Fi 4 or Wi-Fi 5. The difference between these generations is mostly there are many features, right? Each of these blue boxes, which I don't think you can tell what it is, but essentially there are capabilities that we add generation to generation. Up until Wi-Fi 7, most of the effort has been on increasing capacity. People always look at wireless and say, this is slow, right? That's the first thing people say. Well, it's really slow. So a lot of the work that we've been doing is, since Wi-Fi 1, okay, is trying to improve the capacity of the network, make it faster. The simplest way to increase capacity is by doing what? I mean, if you just look at channel capacity theory, right? So it's double the channel bandwidth. So if you look at Wi-Fi, we've gone from 20 megahertz channel bandwidth all the way to Wi-Fi 7 today, where we use 3 to 8 megahertz channels. That has led to a capacity improvement, and that's what you see on that plot on the right-hand side. I don't think I have a pointer. But if you see that plot on the right-hand side, you see that we've gone from Wi-Fi 4 at about 300 megabits per second. Today, newer, if you buy laptops today, most of the new laptops, they are capable of going to 5.8 gigabits per second. Okay, so the capacity has increased, about 500 times in 20 years. If you look at any other wireless technology, or wired technology, I mean, well, I wouldn't say wired, but yeah, even wired, because if you go from Ethernet, we have 1 megabit, most of the time today is about 10 gigabits per second Ethernet. I don't know if you guys have followed that. We do have 100 megabits and, even 1 gigabit, but the pace at which Wi-Fi has evolved from a capacity perspective has exceeded many of the other communication technologies in this time frame. Okay. So it has been often about increasing capacity and make it lower latency. People use Wi-Fi today for conference calls, right, video calls. And so the ability to not just have more throughput, but also do it in such a way that the latency is manageable so that when you're on a conference call, your voice is not lagging, the video is frozen, right? So the ability to be able to send packets on a predictable fashion is something that we've been working on for the last 20, 25 years. And this is Wi-Fi today. Okay, if you get your, for those of you who have iPhone or Samsung Galaxies or newer laptops, most of them today have Wi-Fi 6. That was the first time from the communication technology that introduced OFDMA. Up until Wi-Fi 5, Wi-Fi was simply OFDM technology. OFDMA is what they use also for cellular communication. And Wi-Fi 7 was just launched December of last year, right? So there are devices in the market, but of course, it's going to take time for that to penetrate the mass market. Okay, so, and by the way, if you have questions, feel free to raise your hands. We don't have to wait to the end to answer any questions. So this is Wi-Fi today. So what I'll talk to you next, and that's the focus of my talk, is really about the future, as I mentioned. And most of the Wi-Fi today is what you see on the left-hand side. It always has been about how we can optimize the network. What I mean by optimize the network is make it more efficient, make it more manageable, try to, as much as we can, to manage interference. One thing that you should know is that as opposed to cellular networks, where you have operators in Mexico that they use dedicated spectrum. So in other words, if they own the spectrum, nobody else is using their spectrum. Wi-Fi operates its unlicensed spectrum. So what that means is, in 2.4 gigahertz, for example, which is one of the bands that Wi-Fi operates, you have Bluetooth operating that same band. You have microwave ovens operating the same band. You have some cordless phones, for those of you that you still use cordless phones in your house, that they actually operate in that band too. So there are multiple technologies that operate in the same spectrum as Wi-Fi. So managing interference is a big thing, because we cannot assume that we own the spectrum. We have to deal with all the things that are in that spectrum. And so that has been a major focus. But if you look at the future, we are expanding what we mean by improving Wi-Fi. The main three areas of improvements, there are these triangles that you see on the right-hand side, right? The first one being deterministic. We're going to be talking about each one of those. Deterministic is about that ability to deliver packets on a predictable pattern, right? So that, again, if you have a video call, a voice call, and people are using Wi-Fi today for the most, time-sensitive manners. If you look at industrial, like you have many factories here, we walk by some factories. The ability, for example, to have robots in the factory being able to communicate wirelessly with an infrastructure. But those robots cannot stop. So if your Wi-Fi is not working, people are not going to use the Wi-Fi, right? So there's a lot of work to make sure that Wi-Fi works even for those, high demanding environments. So we'll talk about deterministic. The next one on the bottom right is about more reliable and security, right? So security is a big thing, and reliability is how every Wi-Fi connection today is encrypted, okay, with the most secure cryptographic schemes. But a lot of it's about today is about privacy, right? So security and privacy are different areas. So you can encrypt data, but the ability for someone to track you is something that has to be dealt with. I mean, there is every device that you have today, your phones and everything, they have these hardware addresses. There's some fixed hardware addresses that every time you manufacture, there's an address. Whenever you send a packet to identify you, you put that address in the packet. It's not IP address, by the way. I'm talking about lower level. We call it the medium address, the MAC address. And people have shown that those MAC addresses don't change. So if I go from US to Mexico, if I go to Europe, those addresses are the same. If someone has the ability to be tracking this, they actually know where I'm going to be, or where I am, for that matter, and where I have been before that. So privacy is a big thing that we are trying to address by dealing with these addresses, that are fixed today, but they're not going to be. And then the last one is AI, right? AI, yes, that's artificial intelligence. I think all of you, I don't have to tell you about artificial intelligence. Everybody's talking about it all the time. And we are evolving Wi-Fi to be able to incorporate artificial intelligence techniques to make use of the Wi-Fi. And by the way, I'm talking about Wi-Fi today, but the same thing is happening about cellular or Bluetooth. So that in general communications, right? A lot of communication technologies are moving towards that. But in this case, I'm going to be showing you examples and showing you how we actually tackling each of these areas, in the future. So let's start. The first one is going to be, hopefully this works. Next slide. Yeah, is that the next slide? I think so. I don't know. Can you go one up? One up. One more. Okay, there you go. Okay, so that's what I was looking for, right? So I'm gonna walk through each one of these. I'm gonna start with deterministic. Okay, so that I was just gonna highlight that these ones. Okay, there you go. So why deterministic operation is important, right? Why is that the first challenge that we need to address? I always like to start with an example. The best example for me is a classroom, an environment like this one. And just imagine, we all have gone through and learned physics and math and chemistry and all that. I found it, and I still find it, very hard, sometimes when someone writes an equation on the whiteboard, for us that are actually looking at that equation to actually try to understand the meaning of that equation. How many of you, whenever the first time you saw an FFT equation, you actually look at it and say, oh yeah, I get why this is used for, right? It's, translating from whenever you see the equation to actually know how that is actually used and how that, used in actual systems is very hard. So there are developments right now where people are actually using glasses, AR, VR glasses, so that people can actually teach. So then I actually show you an equation, and I say, hey, actually see how a signal comes in, and you do an FFT, you change that from time domain to frequency domain, and see the signal process that you can do on top of it. So being able to actually see makes your learning much, much easier and stronger. Now, imagine that everybody has one of these glasses in the future. Right? We're talking about 10 years from now. I mean, this glass is already available, by the way, right? So you can buy it. But imagine a future where everybody has one of these devices in a place like this. And every of these devices, it doesn't have a cable. It's going to connect over wireless. The density of devices is going to be significant. And you're going to have to be receiving very high quality, very low latency data. And everybody's going to have to be receiving that same data, right? So whenever you have environments like this, that's where it becomes really challenging to deliver the data in one timely fashion, so that everybody gets the data at the same time, right? So that's why what we call deterministic is the ability to deliver data with a given latency and a given reliability. So if I tell you, you know what, if I go to a factory today, car factory right here, and I say, look, I'm going to put wireless here. The first thing you're going to tell me is, yeah, okay, for these robots, I need to deliver the latency with a 99.99% availability every 10 milliseconds. If you miss a packet, the robot stops. Because robots, they cannot be moving around, without that control loop, that manages the robot. So that's what we're trying to achieve. We're trying to achieve a place where, with wireless, you can say, I'm going to deliver data with a given latency and a given reliability. And so this is why deterministic operation is really important, okay, for these types of operations. Even if you don't talk about video, if you talk about this robot, it needs to send only a few bytes. It's just to say, yeah, I can hear you, okay, yes, and I'm still working. But it needs to go at a timely fashion, every 10 milliseconds. If it doesn't go through, it needs to stop. And so the question is, okay, I understand the use case, I understand why it's needed. What are we doing in terms of Wi-Fi to actually be able to deliver to this type of use case? And once again, slide. Okay, thank you. I hope it resumes. I think it's going to parse it. Okay, so let's talk about multi-link operation. As one major technology, you're going to listen, for those of you that will be in this industry or will try to learn more in the future, you're going to listen a lot to this multi-link operation. So Wi-Fi today, whenever you try to connect to a Wi-Fi network, what do? You go into your phone, you scan for networks, and you see a bunch of networks, right? You see SSIDs, if you like, right? If you go to airport, right? You see SSID for free, the free of the airport, or some operator or something, right? And then you choose one, and you put a password many times. Whenever you connect, you're connected to that network on a given frequency band, whether that is 2.4 gigahertz, 5 gigahertz, 6 gigahertz. Those are the bands that Wi-Fi operates. And you connect and you stay there. The analogy that I like to use is, imagine in a road, if you have 3 lanes on a road, Imagine you pick one lane with whatever, each one of those three. And imagine those three lanes, by the way, they are 2.4, 5, and 6 gigahertz, just like in Wi-Fi, different spectrum bands. Imagine that you pick one, and no matter what, you always stay with that one. You never change lanes. Even if there's huge congestion, the other two lanes there are completely uncongested, empty. There's nobody there. You cannot switch lanes. That's how, up until, that's how Wi-Fi is today, guys. That's how it's today right here. That's how cellular, well, cellular is different because cellular, nobody uses the spectrum. But in Wi-Fi, everybody can use the spectrum. But the idea is whenever you connect to a band, you stay there. You can always disconnect, by the way. But you as a user, to disconnect, when you say you're gonna have to look for another access point and then connect to your access point. It's not seamless, right? You're gonna have to intervene and do something. This multi-link operation basically resolves all that. You can go, as you can imagine now, you can be switching from one bit to the other in the order of microseconds. I'm not talking about minutes, I'm not talking about even dozens of milliseconds. I'm talking about microseconds. I can go from 5 gigahertz, oh, it's busy. I go to 6 immediately in the order of about 20 microseconds. And I can send data. And I can go back and forth anytime in the order of microseconds. So the ways we do this, I'm just going to give you, right? With the power to do this, with the power to be switching very fast, what can you do? These are examples of what you can do. The first example of the talk is, imagine that in the same factory that I mentioned, a robot. Now, as I said, if the robot cannot communicate with the network every 10 milliseconds, I have to stop. Well, you cannot really stop a robot in a factory, right? It needs to keep working all the time. Now imagine the robot can talk to the access point on these three lanes at the same time. What would I do? I will send the same packet on all three. I just duplicate everywhere. Because I know if there's interference on two orders, it's okay, as long as one of them gets through. So it's all about, I want to increase the reliability of my transmission. So I repeat data, and I send the same data across multiple channels. If one goes through, I'm happy. It doesn't matter that the other ones go lost. That's one mode. But imagine another mode, the one in the bottom. That is different. I said, look, I don't care about being reliable, but I'm sending this very large file. It's a huge file. I need to do an upload to Facebook or to TikTok or whatever that may be. And I want this upload to be done fast. Well, I don't send the same packet because it would be wastage. But I send different packets on different links. I send different packets. So I'm basically, instead of being limited by one, I get now 3 times the capacity now because I'm sending different packets over 3 links. Sure, one of them may be dropped because of interference, but I just need to retry that one. Right? I retry later. I can resend it later. But I'm trying to always exploit more channels. What you can do as well is that the other thing you can do with this ability is to reduce latency. So in the same example that I had with the 3 lanes, if I have this congestion of the middle lane, imagine that there is someone, and by the way, the Wi-Fi is someone is the access point, is a network. The network sees everything. And it's looking at it and saying, you know what, this channel is very, very busy. But I have these 2 other channels, there's nobody there. It was very, very quiet. So the access point is dynamically moving devices from one place to the other to try to balance so that everybody receives and experiences the same quality of service from the network. Okay? So that reduces the latency for everybody. And then the last one is when you actually want to do differentiation. The latency improvement is like, it's almost like you can think of it as socialist, management, right? You try to make everybody equal, just try to improve for everybody. The traffic separation is not socialist. That's more like, well, I have this application like a Zoom call, for example. Zoom is more important than anything else. So I'm going to dedicate one channel just for Zoom because it's so important for me. I want everybody to have a great call here. But for everything else, I don't really care. I can let them go to other channels, right? So it's about prioritizing traffic to different channels. Now, with all these, you can make Wi-Fi a lot more deterministic, and we have shown actually that it becomes a lot more deterministic with all these with this capability for multi-link operation. You can optimize it for different performance metrics. I'm going to need your help again. Oh yeah, there. Okay. All right. Okay, so that's about deterministic. Now, the next thing is about what we call AI enabling. So AI is a big thing, right? The question that we want to answer is, how does AI that we use that for, I'm sure you guys all use ChatGPT and all those things. How does that have to do with Wi-Fi, with communication? I mean, why would we use it? There are people that are looking at the use of AI for communications for different things. Modulation, for example. That we look at modulation. How can we change modulation, on the fly, right? We have devices to be able to be very dynamic when it comes to modulation speeds. What I'm going to be talking about today, it's not about the communication system itself. How can you use AI for the communication system, but rather, how can we use communication, in this case Wi-Fi, as a sensor? Okay. So I don't know if you know this, but the average number of, just think about how many devices wireless you had in your house 10 years ago and how many you have today. You probably have observed, if you think about it, that you have so many more devices that are wireless than there were 5 years ago in your house. The average number of wireless devices in a home, in the US at least, I think Max is probably not too different, is about 20 today. Okay? 5 years from now, they say it's going to get to about 30, over 30 devices. So you have a lot of devices in your house that are wireless. Imagine that I can use those devices not just for sending data, but as sensors. What do I mean by sensor? If you have police cars on the roads today, they're trying to detect that you are speeding. What do? They stay parked somewhere, they hold a radar, right? And they keep pointing that radar to the road so that they can try to see the speed that you're at, right? The way it works is you send data, you get data back, and you measure the Doppler, right? And with the Doppler, that's how you say, okay, that car is coming in at whatever, 80 kilometers per second. Imagine I can use Wi-Fi, right, and any wireless technology that used today for data, sending data, as a sensor, to implement a radar, for example. But instead of a radar that goes all the way far away, like detecting a car, the speed of a car, but it's local, it's just around you, because Wi-Fi is just local, right? It's just in this building. And I can detect in your house, I can, for example, detect that someone opened a door to a given room, or that there is someone that is walking in a given bedroom in your house. Imagine I can implement security systems. When you leave your house, your devices are there. I mean, your Wi-Fi devices stay in your house, right? They don't go with you. Access point is still there. Imagine somebody opens the door, gets into your house. You get a message on the phone that says, hey, somebody opened the door. So you know that, there's somebody there. There are companies that are actually selling this service already. Because you have so many Wi-Fi devices in your house, you can use them as sensors now. Nobody's saying, nobody accesses the internet, the house is empty. You can use those devices. So there are a lot of use cases. I should try to go to the next slide, hopefully. This one, there you go. So there are two major categories of use cases that you can think of using that I'm going to be talking. I'm going to show you how you can use Wi-Fi today. One is sensing, the other one is ranging. What are they and what is the difference? Sensing is about, all of them, they are local, right? Nearby you. That's what we call context-aware experiences. But sensing is about you making gestures and the device reacting. Today, you interact with devices with what? With touch, right? You can touch, you can speak to a device, right? You have a mouse, that's another way to, the keyboard. Imagine they could actually make gestures now. So, you have a screen, you have your TV, And you could say, you could do this in front of the TV, goes from one channel to the next. Okay? So you can actually do that with Wi-Fi. The ability of the device becoming smarter and knowing what's around you and waking up when you approach it. And for example, if you leave the device, you forgot the RPC unlocked, automatically detects, oh, there's nobody there, locks the PC. Because, you know, it's a security hazard if someone comes and tries to use a device. It can measure your heart rate. We can actually measure, breathing rate and heart rate with wireless technology. I'm using the same radio to measure breathing rate. And just think about it. Another use case is measuring elderly fall. Right? If you're in your house, you have your mother, like I have mine, that it's pretty elderly. Imagine that I could actually have a device that detects through Wi-Fi and machine learning. By the way, all these, there's going to be some machine learning to figure out what's going on. Wi-Fi is going to give you the channel. The machine learning is going to look at the channel and figure out, oh, okay, this was someone making a gesture to them, making whatever, right? Doing whatever, or somebody fell down. So Wi-Fi is going to give you the channel, but then you're going to have signal processing on top of the channel with machine learning to tell what is actually going on. So that's the sensing. And then the ranging. Ranging is different. Ranging is about, you have two devices. Doesn't have two, or have, just like here, I'm sure all of you have phones. But I could actually figure out the distance and the orientation from me to every one of you. I could actually say that this device is 30 degrees, okay, from that other device at 2 meters distance. And you can think of it, okay, why do I need to know that? So they need tons of use cases, tons of experience. You could get your laptop to an office and you can project right here. I mean, I could project just by getting my laptop close to that display right there. If I had multiple displays, I would know which one is closest to me. If I want to duplicate my screen, we do duplicate screens, right? I need to know which one is right, which one is left. Well, if I have the orientation, I will know this. So I'm not using the Wi-Fi to send data. I'm not using I need 10 megabits per second. No, that's nothing. That's the thing about this, right? There's nothing, it's not about speed. It's about using the radio to figure out what's happening, what's around me, and are people moving around me? How many people are around me? I can count number of people. Okay, and I can control, for example, ACs or temperature or do so many things because I know how many people I need to move. All right, so there are different ways to do sensing. I'm going to talk sensing and ranging. Sensing is, let me talk about sensing first. There are different ways, different modalities. We don't have to go through all of them. I'm going to talk about the first one, which is called monostatic sensing. This is what police uses in their cars, okay? It's monostatic, meaning all I need is the police holding a radar, and it shoots a signal, gets it back, and when you get it back, you can then, in this case, figure out speed. In our case, we can figure out speed too, not at the same granularity that they do because we don't have that much bandwidth and power. But we can figure out whether things are moving in a house. And I'll show you an example in the next slide, what we can actually do with it. There are other modalities that are going to be really important in the future because you have this radar case is just one device, right? One device doing everything. But imagine if I have in your house 20 devices. I can leverage all those devices to do sensing. Okay? But I'm not going to be talking about that today, although that would be another talk on its own. Okay, so this is a video which I hope, okay. This is an example of sensing, okay? And I'll try to walk you through what's happening there. You're gonna see the laptop, there's nobody in front of the laptop, right? And this person comes in, it detects the presence of the user and wakes up the computer. Okay? You don't have to do anything, the computer wakes up by itself. It If you walk away, you see your PC is unlocked. Left the screen there, right? It actually detects the absence of a person. And it locks the computer. If a third person walks by, you see it's walking by, the laptop knows it's not coming towards me. They detects somebody, but it's not coming towards me. Like somebody comes towards you, then the signal wakes up. Okay? What is happening here is essentially that the Wi-Fi device on that PC is acting as a radar. A very short-range radar that is detecting the absence or the presence of someone. And this, again, is a very simple example. You can do this in a whole house, okay? Because you have Wi-Fi signals traveling through your house. So what's going on here? Now, if I go into the details of what we're actually doing to implement what I just showed in the previous slide. If you're familiar with, signal propagation in wireless, right? It's a multipath channel. So whenever you send a signal, the signal is going to reflect, right? It's going to bounce off different objects until it gets to the receiver, right, on the other side. What we are doing is that we are estimating the channel. FFTs, that I'm sure all of you are familiar with FFTs, right? That's what we use in communication systems. We do an FFT, and what we end up with is what you see on that bottom right side there. Every bar, if you will, every curve that you see there is one FFT. We do an FFT, and each one of those, we are estimating the channel. We are looking at the channel, and that's what we call the channel impulse response. This is what Wi-Fi is going to give you. It's going to give you the channel impulse response, and we basically smooth out the channel. We feed that into a machine learning algorithm, just like ChatGPT, but of course, it's not trying to do any text generation or anything, right? It's a given purpose, which is we feed the channel. We have trained that model, that machine learning model, to detect the presence of absence of someone, so it's trained. So we feed the channel, it takes the channel and says, yeah, there's somebody here. Well, no, there's nobody here, right? And that's how we can tell. It's a mixture of wireless communication, the signal processing that we do on the signal, feed into the machine learning algorithm, the model, and that outputs, what's actually happening. You can do this for anything. I mean, as long as you have the model, you can do this for gestures. I want to detect, these gestures. Okay, fine. You train the model, you have to do the training, have the model, you do the CSI, what we call the channel state, you feed into the model, and you can tell you what's going on, right? It's a lot more complicated than this, but that's the idea. That's broad strokes at what we're doing. So that was sensing, right? You have a radar that's just trying to sense the environment. Ranging is different. I'm trying to measure distance. Now, distance and orientation. The way we do it is by, if you see the math, it's very, very simple. It's just time of flight. I mean, we all familiar with time of flight, right? So if you know how much time it took from you and you back, and from you to me back, I mean, I know that waves, they propagate at the speed of light. I can say, yeah, by the way, that's what these radars from police cars, they do. That's all they do. I mean, they do Doppler, but they look at this time, how much it took, and they look at the frequency change, and they say, oh yeah, this car is going at whatever speed. The challenge for us to do that, radar is a very dedicated device. It's all it does, right? The hardest. Here, we have to do so many other things. It's a much more complex system. And so, whenever you receive a signal, it's very hard to send something back immediately. You have to receive, you have to process the signal, you have to know what that signal is, and it goes through several steps before I send back. So there's a lot of uncertainty and bias in the way that you do the measurements. So it's more complicated from an implementation perspective, but essentially that's what we do. And then we calculate the time of flight, and we know how close you are, right? To some of how two objects, how close they are. The other thing that it does is that this system is also very secure. So I'm going to use the example that I used, the other time. Key fobs. Many people have cars today, key fobs, right? So you get close to your car, you don't even have to get your keys. You just hold the handle of the car opens, right? Very popular. And then, the same likewise, when you leave the car, you lock the door, you touch the car, it locks the car, and you just leave. So the way that system works is whenever you touch it, you have a system in the car that is trying to measure distance. That's what it does. It sees how close their antennas outside the car, how close they are to your to the key fob. If they're close enough, right, they open and close. There are some thefts in the US, maybe here too, I don't know, but in the US for sure, because it's YouTube, you can see on YouTube. There are thefts that people were able to go to your house and people leave their cars outside the house. Your car is parked outside the house. And of course, when you go into your house, you take your key fob with you, right? You go into your house, you put your car keys, on somewhere, right? Your car is outside. What the thieves will do, they will be always in pairs. Two guys. One guy will be with a big antenna next to your house, maybe by the door of your house, by the windows. The other guy will be next to the car. What they are trying to do is, the guy with the big antenna next to your house is trying to pick up the signal from the key fob on one side, and the other guy in the car, he's holding on to the car handle. Okay? What they're trying to do is, whenever the car detects there is somebody holding the car, he's going to try to measure the distance and say, hey, are you close to me, right? The key fob, are you here, right? That signal would propagate to the guy with the big antenna with the big power amplifier, and it would propagate and amplify the signal from the key fob to make it seem like the key fob is right next to the car. And they showed like people were able to steal cars, numerous cars in the US, just by doing this. Because the system was very good, very convenient, but was not secure. Okay? Because you could actually make it seem like the device was very close to you. So having said all these, you don't have to worry about Wi-Fi because we actually done it. And we've defined a secure system that you're gonna have a key that is negotiated between the car and the key fob. So that thing changes all the time. So this attack is no longer possible. But I guess I'm just showing you, it goes to say, how this whole security aspect is very important, right? And people actually have material, impacts on people's lives. Okay. All right, so this is one more example, one more video. Now, this is not the sensor, this is the range. What we're gonna see here is someone with their phones in their pockets, in their hands, walking close to the laptop. And what you're gonna see is that it's gonna unlock the laptop as you get about half a meter. And if you go beyond half a meter, it locks the laptop. So there you go. He's holding his phone in his hand, by the way. See, the phone is on the table right now, so he's working, right? Automatically locking, he's gonna walk away. Took the phone, so the computer is locked now. Okay? So that's what we're doing on the previous slide. We are essentially calculating the time of flight in a secure manner. So that you can log in and log out. Okay? Using the Wi-Fi in your system. All right. So this is about, again, all this is about we use machine learning together with the communication, we are merging them together to provide this level of intelligence now. So you see, I haven't talked about data rate, I've been talking about, so much faster. No. The speed is not the point here. The point is, how can we make it smarter, more deterministic, which we talked about before. And then the last one now that I'm going to talk to you about now is, how can we make it more reliable? Okay, and with better privacy. So, reliability, okay, there are many definitions for reliability. So there are many definitions for reliability. It can be, I talk about, 99.99%. People say, oh yeah, I need to be that reliability from the given latency. Another way to think about reliability that people complain a lot is man, the signal is so weak, when I go to the, if I'm in the bathroom of my house, or if I go to a corner room, man, the signal is so weak here. Well, I'm sure you know, right? All this is regulation. By regulation, you can only transmit with the given power. You cannot exceed that power level. And so at some point, you're going to experience big signals, so that's a fact. But, for those of you that are familiar with, regulations, right? There are things that we can exploit in the regulation to be able to give us better signal-to-noise ratio. And that signal-to-noise ratio can be translated into data rate or can be translated into range. So I mentioned to you in the beginning that take a Wi-Fi channel band for about 20 megahertz. Okay. As you go into 20, and then we go into 40 to 80 to 160, regulation, it can be written in two ways most of the time. In the power spectral density, or what you call the ERP, which is the maximum power that you can transmit. Well, the way it turns out is that you can think of it as you have a given amount of, let's say, water. Right? You have water, let's say you have 1 liter of water. If you drop this 1 liter of water in a channel that is this big, it's going to fill up all this, right? But imagine now that I tell you, you know what, you can use a channel that is 4 times this. So, you make this bucket so much, bigger, right? But it's the same power, the same amount of water. So what's going to happen? The level of water is going to drop, right? That's the same thing that happens with wireless. I have a given power. If I keep on increasing the bandwidth, if the regulation is written in such a way that this ERP, I'm going to have to drop the power. So yeah, I'm getting more bandwidth and I can get higher data rates, but only for people that are close to me, because I have good signal-to-noise ratio. For the guy that's far away, if I use those big bandwidths, it's not going to help. Why? Because the power is going to be so much lower. Then you're going to say, oh man, this is so slow. But one thing we can do, and we are doing, that depends on the regulation, is instead of, that's the smart thing that we are doing now, right? Because everything that I said in this example is still valid, but I'm only thinking of one user. And I say, look, I can transmit 20 or I can transmit very wide. But in practice, I have 10 users in a house, right? And actually, when I have 10, 20 people, I have to transmit to a bunch of people at the same time. What I can do is I can now spread the power. I have the same power, but the way I'm going to do is, if you see the figure on the left figure there, one way I could do is I can focus the energy in one place, or I can spread the energy. Now, the regulation is power spectral density. It measures the density over 1 megahertz. So if I transmit a lot of power together, I'm going to have to back off on my power because everything is so close together, the density is very high. But if I spread the energy, the density per megahertz is going to go down. So I can essentially increase my transmit power because now I'm spreading the signal, and I can decrease the transmit power over that density of over the megahertz. So we are doing this. It's giving better range. Okay, you can see all the green numbers at the bottom, up to 10 dB greater range in some cases, because I'm actually, being able to spread the signal. The other thing that we do, what's this one? Maybe this one, sorry. Here. Oh yeah, there you go. So I don't know how many of you have, I'm sure all of you have access points in your house. I don't know how many of you have more than one access point. In some cases, it's becoming very common. I mean, in a place like this, for sure they need to have more than one access point because it's a big location. But in your house, many people have just one. Having more than one is becoming, again, very popular. All these access points, they don't coordinate with each other. There's no coordination. You basically assign them to one channel, the other one to the other channel, they forget about it. As long as we don't use the same channel, there's no interference. Well, in practice, this works when the number of channels is greater than the number of access points in a given location, right, in a given vicinity. But reality is that you always have a lot more access points than you have channels. And then you have to reuse, right? You have to reuse channels. The moment you reuse channel and you're not too far from each other, you have interference because you're reusing channels, right? And so today, there's no coordination. You can have one access point using the same chain as another one, they will collide. You're sending packets, there may be interference, okay? So what we do here, this multi-IP coordination now, again, this is the future. It's not available today. I'm talking about 2031, 2030, 2031. These access points are going to be able to coordinate at the level of microseconds. And they're going to be able to take turns or use different portions of the spectrum. So if I go to the next slide, the ways to share, if you have a resource, a spectrum resource, you have ways to share it by frequency. That's the first diagram. What I can come here. You can share it by frequency. Each one takes a piece of the channel. But they have to coordinate. They have to say, you use this piece, I use that piece. They can share time, right? One uses one time, the other one uses the other time. And then there's no interference. Or in the last one, space, right? So everybody can transmit at the same time, at the same frequency, but they are so far away from each other that the SNR is good enough that I can transmit and they can transmit. And we're going to be fine, okay? So these are the levels of coordination you're going to see in the future with multi-AP. Okay, so the other thing that I'm trying to go this quickly because we are running out of time is the way that Wi-Fi works today for historical reasons. There are many reasons, okay? But the way it is today is that if you have a big fat pipe, right, this is the channel. If somebody grabs what we call the primary channel, you're going to have a lot of unused spectrum. Okay, so you can have like 80 megahertz, but you have that, you know, thermostat, that IP camera that only uses 20, doesn't need more than 20 megahertz. It grabs the 20 megahertz, and then it wastes all the other 60 megahertz. What we're going to be doing, again, as part of the future, is be able to, you know, make use of that today's unused spectrum. Okay. And by the way, we're talking about orders of like 5 milliseconds. And so every box that I draw here, that's a packet, and every packet is usually anywhere between, you know, 1, 2, 3, up to 5, 6 milliseconds. So that's the order of magnitude that we're talking about. And that's what we have, that's what I'm showing here, but you know, I'm not going to go into details, but that's what I'm essentially showing how in the future you're going to be able to split devices into frequency, you're going to be able to make use of these unused portions of the spectrum, and basically increase the efficiency of the network, the bits per second, the hertz that you can send over the channel. And then my last topic, that's my last topic of this talk, is around privacy and security. You know, there's lots to be said here, but the main point that I want to maybe convey today is what I said earlier, which is every device today that is shipped, whether it's Wi-Fi, Ethernet, your SIM card on the cellular network, they come with an address. And that address, that's why you have to take a SIM card, right? People know, oh yeah, that's you, because you know, I have a physical address there. That address is fixed. If that data today is just being open, people can track you wherever you go, because that data is sent in the open. So what we are doing, and again, this is being worked on as we speak, is to be able to change that data, but you see, it needs to change for other people so that they can track you. But the network needs to know it's still you. So it's like, we cannot simply go to a mode where, oh yeah, we can change all the time and that's easy, oh, we solve the problem. No. Because then, if the network wants to know that, hey, this is actually you, because it needs to know to authenticate you. If you are changing all the time, I don't know that it's actually you. So it's a mix of, I need to change it for other people, but for the people that really need to know, they need to still see that physical address, yeah, that's you. Right? And that's where the challenge comes on security, right? It's being able to defend against other people, but the people that actually, you know, need to know that it's part of your network, right? They need to see that it's regional. Okay, all right. So that's my last slide. I have a conclusion slide here. There you go. So, hopefully I've been able to give you a feel for where the technology has come so far today. A lot has been on increasing capacity, reducing latency, making things better, faster, right? But in the future, it's all going to be about, and I can say these for other technologies too, okay, cellular included, it's going to be all about how can we use these radios more than just anything? Using them for being aware of their surroundings, being aware of, when I say surroundings, it's not just people's or anything that is moving, but also other devices around me. Okay, by knowing where everybody is and devices are around me, I can actually deliver so much better experience than I can do today. Okay. All right, so that's all I have, and I will gladly take any questions if you have any. So thank you very much.
Una pregunta para el doctor. Puede ser en español o en inglés.
Yeah, español is bueno.
I have a question. Referring to the future, as you said, one of the topics I'm interested in studying right now is quantum computing. Have you seen any potential advantages, disadvantages? And if you have, which ones are they?
Yeah, so that's a great question. From a quantum computer point of view, the aspect that we are looking right now is post-quantum cryptography from a communication perspective. We're actually not looking at it's still computing, but computing the director of security. It's interesting because just this morning I was having communication with someone in my team and we were talking about this, right? So we are trying to define new cryptographic schemes that will be secure against future quantum computers, because all the cryptography that we use today, they can be broken by a quantum computer. Okay, so that's the angle that we are looking from a communication perspective. Is most of the security aspect of communication. Yes, please.
Yeah. Thank you so much for the presentation. I have a question about the maybe off topic, but about the good speed in the internet. What is the infrastructure I need in Mexico? A fiber optic or coaxial and fiber? What is the best infrastructure?
Yeah, so definitely a different topic, different question, but look, if I see how the infrastructure is evolving, not just, in different places in the world, right? There's definitely a much stronger fiber rollout. Let me use China as an example, so that people don't say I'm biased. In China, they are taking fiber, what they call fiber to the room. They're actually deploying fiber not just to your house. They actually, from your sidewalk into your house, they are making sure that they have a fiber connection to every room in the house. Right? I would say that you can argue that if you look with the eyes of today, there's an extreme, but I think fiber is very expensive to deploy because you have to break ground, right? You have to break ground to deploy fiber. But that sort of gives you an idea of where I think 10, 15 years from now, right? Places, countries that actually have that foresight, those are definitely going to have an advantage over other places, right? So in US, they have a focus on taking fiber, to your sidewalk, right? Or to certain, they call, POPs, right? Points of presence. So I think fiber is definitely a big thing in Europe as well. There are major efforts in deploying fiber. And then, look at coax. You can still use coax, right? Coax is usually mostly used from the fiber point of presence, right, into people's houses because it's much cheaper, right? And then once you get to your house, what do you use? You want to use Wi-Fi, because that's going to distribute the capacity over your house. So there's a hierarchy, in my view, that, it's fiber, definitely through the major to distribute capacity all over. And then, yeah, you can use coax. Okay, China is using fiber even to your home. That's, it's a choice. But then to distribute capacity, you're going to use Wi-Fi. Look, there's a role also to be played for, I don't want to dismiss anything, cellular, right, and fixed wireless. There are places, especially remote places to get to. It's very hard to get a fiber to remote places, right? Villages, and I think fixed wireless has a big role to play there because it's cheaper, right? You don't have to run a cable, my fixed wireless, you can actually have very high capacity. So look, I don't think it's one technology, I think it's multiple mediums. And, Mexico is such a diverse place. I think in urban places where you have very high density, you need fiber. As you go to more suburban places or rural places, you can probably get away with less fiber and more fixed wireless.
Thank you so much. I have another question about the extensive. When you got your computer unlocked, Apple may may similar with your Apple Watch.
Yeah.
This is with any device or only Android, Windows device?
So the technology can be used for any device, right? In principle, it's just a technology. Anybody can implement. What Apple did is over Bluetooth, by the way.
Yeah.
Right. They use Bluetooth and they use RSSI, so they can actually use the distance. It's a RSSI is like the signal strength. It's a proxy, but it's very inaccurate actually. So it can be very unreliable. Here we actually measure the distance, so it's a lot more reliable. Because you can be very close to someone, have very low RSSI, because maybe you have a wall, right? It can be very close to you, but if I have a wall here, the signal is so weak to her, that's gonna say, oh, you are 20 meters away. No, I'm actually 30 centimeters away, right? So RSSI is very unreliable. But if you measure the distance time of flight, it doesn't matter. Even if the signal is weak, it's just time of flight. So I don't know if I take it.
My last question about what is the bounding box the Wi-Fi to detect distance? The bounding.
It's like depends, right? If I'm trying to detect, for example, presence to like getting close to the use case that I showed to a PC, I just need like 2 meters around the PC. I don't need more than that, right? But if I'm trying to detect movement in a house, I need to cover a much bigger space. So it depends on the use case.
Okay, thank you so much.
Another question?
¿Alguna otra pregunta para el doctor?
We have about APIs for work.
I'm sorry, say it again.
You have APIs for work with the Wi-Fi?
Oh, okay, APIs.
API.
Okay, got it. For which, so we do have APIs, number one. But I think your question is more, are those APIs public for anybody to use? I think that's really your question. Look, that's a business question. Sometimes we make the APIs open. We usually give source code for people to use. We have done that many times. For this technology in particular, because it's new, we are releasing this to certain partners, certain OEMs. So we're not making widely available because it's new. There's a lot more interest, and so they try to control it. So, but we do have APIs not public right now for anyone to use. But having said that, we do make available our driver that you can extract the CSI. So if you have students that understand communication, and we have many I mean, there are many papers. If you search on the internet and Google Intel driver CSI, something like this, you're going to find many papers written where people have written papers using our drivers to extract CSI and then do other things with it. So I mean, you can but then it's up to anybody to go ahead and use it, right? In this case, we are using for our own purpose, and we have our own way of treating signals. Thanks.
If there is no more question, thank you very much. Thank you very much, Dr. Cordeiro. I present you with this award from Senate in recognition of your interesting talk, and also this present for you.
Thank you very much.
We hope to have you here in the future.
I hope so. Thank you. Thank you very much.
Gracias. Enseñando.
Oh, sorry.
Eso sí es.
Muy bien. Gracias.
Ahora con el confesor.
Sí, con gusto. Sí, sí, con gusto, con gusto. ¿Encendemos la luz?
Sí, por favor.
Gracias. Para que estén viendo. Pero vamos a apagar. Y apagamos
Nada más baja.
Apagues el. Pero esto ya una.
Oh,
Sí, sí, nada, la tapita. Otra vez.
De hecho, ya están marcando. Perfecto, gracias. Muy amables.
Chicos, una foto todos juntos.
Sí,
Ah, sí, qué buena onda.
Un poquito más.
Más, aquí, más hacia acá.
Un poquito eso. Qué emoción. Un poquito más.
Acá atrás hay espacio.
Otro poquito. Gracias. Perfecto. Gracias.
We've done that project installed. The problem is that we would be spending more energy to transmit than to actually to recharge. So it was like here recharging was the net it was more energy because we're transmitting a lot more power. So I said, look, this technology is true. So it's not happening commercially.
Yo creo que no, yo creo que no, yo creo que no. Es de nosotros. Ajá. Yo creo que este es el de nosotros. El de
Ah, sí, porque
comunicación,
él estaba
y es el
ocupado.
que están ocupando. Sí.
Perdón.
No, por eso se llama modulation.
Sí, sí.
You're gonna need, if you try to do something, very because you need to transmit and get the signal back, right? And that ping pong, receive and send back, it needs to be done very fast. Because the longer that I take to respond, the more uncertainty the match has. So you're gonna see like, you see matches and you're gonna see have a lot of error. You're gonna have a lot of spice in that. Oh, you're close, you're far, you haven't moved anywhere, but because, why? Because your internal process, if it goes through software,
Ajá, esa, porque la otra es
becomes
de
unpredictable. There's always latency. So get it needs to be very predictable. So we do it in hardware, so they can receive it, do some processing because you need to send something back. And that time that it takes used to be predictable. We do have hardware available, but it does. But if you're trying to take like existing hardware, it's very tough to do it because the moment it goes into software, it becomes very unreliable.
Y después en otra transacción aparte, este es el código que les di para que se haga también. Sí, aplicación. Es ¿verdad? Sí, luego el de estudiantes y el de profesionistas es
de la voz.
pero los códigos te acepta el sistema de hacer un solo código de transacción. Entonces yo les digo, si tienes interés en otra sociedad y tienes otro código, aplica ese código a la sociedad, otra transacción aparte, aplica el código de control, ya es
Oh yeah, there is. There is work that is trying to, use that present to do better error correction.
Yo ya no pertenezco a computación. Alguna vez fui miembro de las dos.
So that you can correct bit errors, okay? Better than you can do with, hanging case, for example.
La dejé.
So
Pero ¿cuál es el
there is a lot of work happening on modulation schemes. Okay, how can we, even develop, change the modulation to better address the challenge? Today we have fixed modulation, right? Like 64.1 with PSK. So people are looking at how can we actually real time develop modulation schemes that have not even been implemented in hardware, but because the AI can actually interpret that new modulation scheme based on what's happening on the channel. So I mean, yes, there are different, of course, for security too. People are trying to use AI as well as to break.
Si tú entras al espectro y le dices, bueno, quiero comprar el paquete mensual, creo que por $18 ya puedes cambiar.
Thank you very much.
Porque eres miembro de este.
Thank you very much.
Tú entras como un miembro, ya puedes hacer el tipo de paquete, todo lo que hayas investigado sobre eso, pero es parte, sepas que eres el para solo para
Si él está interesado en publicaciones,
ahí sí de todo, ¿no?
La otra.
Yes, the backpack.
Se pueden inscribir como estudiantes, ya son miembros, pueden acceder a esa posición.
Okay, high density. Okay. Thank
Digo,
you.
además tenemos ahí.
Para los programas que
So,
son
there are a few ways. One is FDMA. But essentially, because sometimes you have a lot of data, but instead of serving one at a time, you can serve that takes a lot of data. So FDMA sort of breaks the chain with this. Yeah, I mean, yes, like we call it resource units. So you have a 20 megahertz, 40 megahertz. You can then say, now you're going to have like 4 megahertz. Then you can serve multiple users at the same time, instead of serving one at a time. So you have 20 users. You have to wait for 20 people. Well, imagine that I could break it up into 20. So everybody, yeah, you're going to get less throughput, but you're being served. You can add more antennas. Some of the more antennas. You know, you can reduce the cell size and then have more antennas. If you want, like sellers, base stations, they have a very wide ranges because they want to cover a lot of area. But imagine now that if I want to increase capacity in stadiums, I reduce the power. But then I put a bunch of more access points. See what I'm saying? So I reduce, I made everyone very small, but then I put a bunch of them. So now I can serve more users now because, you know, I basically reduce the cell radius. Right? So many more cells now. So there are many, I mean, there are many ways to increase the channel capacity, the channel bandwidth. You can better spectrum reuse, better use the channel, you know, the spectrum you already have. I don't know if any help you or if I confused you. Yeah. Sí, sí.
De computación.
They're trying to use Wi-Fi or trying to use the cell? Are they using the Wi-Fi or the cell?